We all know that indexes help in improving query performance. So when we create an index, we expect that the total execution time of the query will come down. Indexes are essentially searching mechanism. They help the SQL Server engine to get to the data faster, which results in the overall improvement of the query. And what we do is we go and look into the status bar, and we look into the total elapsed time, and we expect that it will come down. Nothing wrong with that. That's all great. We all love indexes. But there is another aspect to indexes, which is the memory grant for your query. Now, when you fire your workloads, or let's say you are simply running a select statement, each query requires memory for its execution. Now, I want to use this word called normal and abnormal, but technically these are not the right terms to use. But let's say the normal execution of your query would require 1 MB, which is the default memory that every query asks for from SQL Server. But there is extra memory that your query might need if it's using operations like sort or hash, or even when it is executing in parallel, the exchange buffers may ask for it. This is called as memory grant, or the extra memory that your query needs. Now, if you're watching this video in the YouTube channel, search on resource semaphore. I've explained this concept earlier, the concept of resource semaphore wait type and the excessive memory grant that your query might need. Or if you're watching this video in our video lobby, you could search again on the same term. Either way, you should get a few videos that will explain you this concept of resource semaphore wait type, and then your query is waiting because it needs that extra memory and SQL Server does not have enough of it. So your query has to wait for other queries to finish before it can get that extra memory grant. So the concept of extra memory grant, resource semaphore is one thing. And now in this video, we are talking about how indexes can actually help your queries to reduce that memory grant. Which is, and this is not going to happen, let's say, automatically. Like you just create an index and suddenly the query, which was, let's say, asking for 1 GB is now just going to ask for 1 MB. No, not that. You all know behind the scenes what's going on. In the query, you have these operators, as I just said, which is like the sort or the hash. When you create the right index, you are expecting that these operators will go away, which are these extra memory consumers. They will go away, and then the memory requirement of the query is going to come down. Wonderful concept. So this video is a little different. Here we are going to create indexes, and I'm going to jump into the demo shortly. We will create indexes, and what you are going to, we are not going to focus on the elapsed time or the execution time. So don't expect that we're going to look at the overall query performance. We are going to look at the memory consumption of your query before the index and after we create the index. Now, before we jump into the demo, a very important question comes to my mind is memory grant, memory execution. So in the overall scheme of things, how does it really help SQL Server? Well, if you look at it, it's a no-brainer because SQL Server has a limited amount of memory. And when you have these queries, these workloads that are asking for this extra memory grant, like hundreds of MBs, and it can also run into GBs, tens of GBs, which I'm going to show you in the demo now, SQL Server will obviously have a finite amount of resources, which is if a few of these bad workloads come into the system and are asking and really hogging memory that way, SQL Server is going to have a tough time sharing these resources like the memory with other workloads, which means a rogue workload can come in and just ask for like tens of GBs of memory, and other important mission critical queries and workloads might be waiting. And SQL Server needs memory, just not for your workloads, right? It needs memory for its engine, for background threads, for other user threads, buffer pools. So many different memory clerks and memory consumers are there in the system that need memory. It is such an important resource, just like CPU, just like IO. Memory is very, very critical. So if you create the right index and help reduce the memory requirement of your query, it's an amazing achievement. Okay. enough of lecture. Let's jump into the demo. So first thing, as always, AdventureWorks 2016 is the database here. A very simple select statement, selecting from sales order header, and we order by order date, descending. So actual execution plan is turned on. Let's go and execute this and jump over to the execution plan. First thing what I'm going to show you is the select operator here. So let's select the select operator, and you are going to see something called as memory grant here. So this is in kilobytes. So you can see the number 16920. So this is about 16 MB megabytes of memory, extra memory that the query has asked for. Now, why? Because there was a sort operator here, and you can see that the cost of the sort operator itself is 80% here. Now 16 MB, so of course sort operator, as I said, sort operator, hash operators, exchange buffers, these are some of the iterators that need all this memory, because sort, and these are in-memory operations, isn't it? Sort has to get all the input, all the data, then it will do an in-memory sort and then send the output to the next iterator. So it needs a lot of memory. And more the data you play with, more the data you are working with, more memory you would need. Same is the case with the hash table. So it has to build the hash tables in memory, and it requires extra memory. So what we can do is, let's say right click and go to properties of the sort operator, and I don't want to hide the properties window, so I'm just going to drag it here. Okay, it went there. Okay, not that place, bad place. Okay, huge window. Let's shorten this a bit. Okay, now if you expand memory usage here, look at this. So we were talking about 16 MB or so. So for the sort operator, you can clearly see input memory, output memory, etc. And let's not get into the details of these memory usage and memory fractions, but in short, it was asking for 16, but it only consumed about 7 GB. So there's 7 MB, sorry. So of course there is some concepts behind how much is it asking for. Is it 1.5 to 2 times more than what really is needed? This video is not the right place to talk about that, but what you can clearly see that the iterators here, like the sort operator, is asking for extra memory. Let's close this one. You know, I'll take a step back and run the select statement without the order by. So of course there will be no sort operator. Let's go and execute this and jump over to the execution plan. And now you can clearly see there is no sort operator. Take the cursor over select and expand this. Now you can see that in the tooltip here, there's nothing called as memory grant. But of course, this simple select statement also requires memory. So that is like minimum memory per query, right? Which is the default. But only when you have these extra operations do you require extra memory grant. That's the point I was trying to make. So in this very simple example, you saw 16 MB, but when your examples get a little more complicated, so this one is another statement. It's not complicated, but all I'm trying to show you is the amount of data. So in sales order detail, the number of records are kind of double or triple, 3 times more, and I'm ordering by line total descending. Let's go and execute this. Just trying to get this concept across to you about this extra memory grant. Jump over to the execution plan. And now you can actually see that this query has run in parallel. So the previous one was a serial execution. There were no parallel operators. And in this one, let's take the cursor over select and then expand this again. And now you can see the memory requirement here is about 30 MB. So double of what we had asked for earlier. So of course, sort and these operations like parallelism. So this is gather streams, distribute streams, and exchange buffers. They all need extra memory. Okay. So now comes the crux of the demo here. We are going to run a workload, something like this. Now there are 2 tables here that I'm going to deal with, which is, where are those tables? Okay, not here. I'm jumping over to the another window. Okay. So I'm going to deal with 2 tables here. Let's scroll up and just show you these 2 tables. So the transactions table here has about 30 million rows, and the big product table has about a few thousand rows. And look at the structure of these tables. Okay, so the transaction table has the ID, product ID, date, quantity, and actual cost, and the product table has a few descriptions and data items related to the product. Now, the reason why I jumped over to another set of tables here is because I really want to deal with large data, big data, and then the impact of this extra memory grant is more evident. And in one of these, now this workload that we are going to run, you will see that it will require more than 1 GB of memory. That, something like what you saw, 16 MB and 30 MB, now will be 1 GB, more than 1 GB. This is what we are going to do. So what I've done is I've written a very simple query here. It's a common table expression, and we are using a ranking function here, row number, and I'm partitioning by product ID, and then I'm ordering by quantity in descending fashion. I'm not putting any filter as of now, so let's just go and get rid of these folks. Okay, not required. Okay, this is the query. And now, just to be sure, there is no index. This will be the second part of the demo where we are going to create the index and to see if we can reduce the memory requirement of the query. So just execute this. Okay, there is no index whatsoever. So let's go and run this query. So we have the CTE, and then the outer query, the select statement, is going to fetch data from the CTE result set. Okay, this is what we are going to do. So let's go and execute this. Now this is going to take some time. This is going to take about 3 minutes. Yeah, the data comes in, but we're dealing with millions of rows here, so this is going to take some time. I'm going to pause the video, and when the execution is complete, I'm going to come back again and look into the execution time. No, not execution time. We're going to look into the memory grant and of course the execution plan. So let's pause the video and come back again. Okay, I have resumed the video because the execution is done. I said pausing the video and resuming the video. Is actually pausing the recording and resuming the recording. Okay, so where we were left, okay, we had executed the query. Don't even look at the execution time because our focus is the memory grant. The execution is done. Let's jump over to the execution plan. And first things first, you will see that this is a parallel plan, a lot of parallel operators out there. You can see the sort operator, you can see the hash match. But first, let's take the cursor over the select operator and look at the extra memory requirement for this query. So this is about 1.3 GB. That's the extra memory grant this query asked for. Of course, it was dealing with millions of rows, and that's why sort operator was expensive. Hash match also requires memory to do its in-memory operations. Now, you will also note here that there is no missing index hint. Typically, when SQL Server has to recommend missing indexes to you, it can do that via SSMS, and you can see those that green missing index hint coming up here. So nothing like that comes over here. Now, I know what I'm trying to do here is play around with some of these attributes like product ID and transaction quantity. And most importantly, when I look at the sort operator, of course, because the ranking function's requirement here is that I'm ordering data by the attribute and I'm using quantity. So if I take the cursor over the sort operator, you can see, look at these two, product ID ascending and quantity descending. This you got to keep in mind. So sort operator here, of course, is quite expensive. And of course, this probably is hogging up a lot of memory out of that 1.3 GB. And the requirement here is product ID needs to be ascending and quantity needs to be descending. I'm also taking quantity. If you can see, this is an additional attribute quantity. And I am talking about product ID also here and quantity. So what can we do now? I will go and create indexes. So let's just one index. So I'm going to create index. So let's go and create an index. I'm jumping over to another query so that I can compare both the execution plans and show that to you. So in the third window, I'm going to create this index, and that, I kind of showed those attributes to you because, okay, so this was actual cost that I was dealing with. Quantity I already talked about. So if you look at the index structure here, the index formation, And I'm reminding you the tooltip there: product ID ascending and quantity descending. So this is a critical requirement here, because we are partitioning by product ID. We are partitioning by product ID and we are ordering by quantity descending. So I do exactly that. Product ID by default will be ascending and quantity will be descending. So these are my indexing columns, right? So this is a multi-column index or a composite index, whatever you want to call it. And then, as I said, I'm using another attribute here, actual cost. So I am taking this actual cost in the include keyword, so that it kind of becomes a covering index there. So let's go and create this index now. I'm going to turn off the actual execution plan. Creation of the index will not take as much time, hopefully will be done in a few seconds. Okay, are we doing it? Okay, let's see. Yeah, so keep this plan in mind and we are going to compare this with the next execution. I'm going to execute the same query again. Okay, index creation is done. Let's turn on the actual execution plan and we have exactly the same query here with try and data. So let's go and execute this now. So this time we are hoping that index, the one that we created, is going to be used and we will see the memory requirement will come down. Let's see what the output is. So let's go and execute this. And again, it's going to take a few minutes for the execution to be done. So let's pause the recording, and when the execution is complete, I will resume the recording. All right, I have resumed the recording because the execution is done. So if something makes you happier here, the execution time of this query here took about 4 minutes, 2 seconds, and the earlier execution was about 4 minutes, 15 seconds. Not a big deal. But anyway, sometimes even a few seconds will make us happy. So let's go and put our focus back into the memory grant, the memory requirement. So this should have been running with indexes. So let's go and jump over to the execution plan, and you will observe, first things first, no parallel plan. So parallelism is out now. This is a serial execution. That's the first thing. Second thing, you can see the sort operator has gone away. Good. Third thing, you can see that hash join has been converted to merge join. I mean, not converted really, but now the optimizer is considering merge join instead of hash join. So those expensive iterators that are, big memory consumers like sort, hash are gone. And the biggest impact here, overall memory requirement, let's take the cursor over select operator and you can see memory grant 1024 kilobytes. Yay, which is just 1 megabyte, the default memory need for each workload. Now, this is wonderful. This is what you would expect and not really the execution time. And think about it. So when you're talking about this workload, which originally needed like 1 GB or more, 1.3 GB, now suddenly does not have that kind of need. And when you're running multiple similar workloads, look at the overall performance improvement of SQL Server, of the engine itself. Hope you enjoyed this demo. So let's just quickly summarize what you have learned from this video and the takeaways. First thing, every query has a minimum memory requirement, which is about 1 MB. And sometimes expensive iterators like hash or sort will require extra memory, which is what we call as the memory grant. And it can really go into hundreds of MBs and even GBs. And you got to identify those iterators. And here what we have done is created the right indexes to get rid of those iterators. And this will have huge impact on the overall SQL Server performance. When your workloads need this kind of excessive memory grant, this memory may not be granted immediately. And as I said in the beginning, when your query is waiting for this extra memory to be granted to it, it might actually wait on a wait type called resource semaphore. And that also maintains a queue, because you might have so many workloads coming in and going out. And when let's say 10 copies of this workload come in, right? And each of them are asking for 1.3 GB, right? The first or the second one in the queue might get the memory, but the remaining ones might be waiting because SQL Server has just limited amount of memory. And only when the execution of the first few ones are done and the memory is released, the other ones waiting in the queue in a specific order will get that memory and they will use it and execute. Okay, we love SQL Server and these kind of demos to improve overall performance. Share it with your friends and colleagues. Hope you have enjoyed. Happy SQL. And don't forget to check out the all-in-one bundle on SQLmaestros.com, where you get all the video courses and all the masterclass recordings packaged into a highly discounted all-in-one bundle. Enjoy. If you like the content, give it a thumbs up, subscribe to the channel and click on the bell icon so that you're notified on new videos. Most importantly, visit SQLmaestros.com. There's a lot of SQL learning resources out there, video courses, master classes, lab kits, ebooks, blogs, hands-on labs, and a lot more. Follow us on Twitter @SQLmaestros and myself _Bansal. Last but not the least, do subscribe to our newsletters. See you soon in another video. Goodbye.